Hey everybody, Dr. Man is back with you to talk to you about charge and oxidation number. I've been talking in past couple videos about like just atoms in general. One fine little bit about atoms is their charge. So I kind of want to talk to you just for a couple minutes about charge. Oxidation number, people misconstrue a charge because sometimes it can be charged, but oxidation number, oxidation state is an apparent charge of an atom within a molecule. A charge is just that, it's the charge. Charges are usually positive or negative, and some people just leave it at that, but I mean, I'd like to explain a little bit more. If you're familiar with magnets, magnets have a north pole and a south pole. Magnets emit a magnetic field. Okay, like you have this substance, and have these field lines going around it, a field of force. And if you've ever played with magnets, then you know that because you can push a magnet across the table, stuff like that. Well, a charge field is kind of like a magnetic field, it's just a field of force around a particle. If it goes in one direction, it's positive. If it's a different direction, it's negative. If you don't have a field, then you're neutral. That's what I mean by these positive charges and negative charges. Electrons are negative, protons are positive, neutrons don't have a charge. Well, they're neutral. Right. When atoms react, man, it's important to pay attention where the electrons are. That's why we care about the charge. Because when they react, think of it, they bump into each other from on the outside. And so it's kind of like eating potato chips. If you have a bowl of chips, which one do you get? The one on top, man. Okay. Same thing for an atoms bump. What's going to interact? The stuff on top, the stuff on the outside, the electrons. So electrons are often lost, gained, or shared in these chemical reactions. And I'm just talking about loss or gain right now. If it's lost, then you make a positive ion. And if it's gained, you make a negative ion. And the positive ion is called a cation. Negative ion is called an anion. If you study electrochemistry, then you understand why they're called what they're called. Otherwise, you just have to memorize it. Okay. Not a big deal. Okay. When If you want an example of that, like calcium cation, here you have a neutral calcium ion. It's losing 2 electrons. That makes the calcium cation plus the 2 electrons that were separated from it. And that's how you would denote it in a chemical reaction. For fluoride, for a neutral fluorine atom to become fluoride, it needs to gain an electron. So they're separate initially, and then the fluoride that tucks that electron down in the electron cloud and makes fluoride, which is why you can't see the electron anymore because it's tucked inside the fluoride. The electron has been gained. To calculate the charge, basically you just need to look at what's going on. If you look here, the one negative here, two positive there, what they're saying is the number of the excess charge. Like a lot of people would write calcium plus 2, and that's kind of wrong. It's calcium with 2 excess positive charges. Okay, it doesn't necessarily mean there's only 2 positive charges, just the excess. For electron, it's a bad example. There's only one negative charge. But to calculate the charge, you use the protons and electrons. All right. And it's kind of neat. All right. All you got to do really is just assume it's neutral and then go from there. All righty. But I have a couple examples laid out from here. Let's use these. If you have 6 protons and 7 electrons, it'd be a 1 negative charge. The reason you're saying that is because you have 6 positives, 1, 2, 3, 4, 5, 6. Each one's hooked up with a negative. So they kind of pair up and neutralize each other, and then you have one extra negative. Well, that one extra negative is why it's a 1 negative. All right. So let's go back to our symbology that was in the previous video. If you have this phosphide anion sitting there, how many protons, neutrons, electrons are in it? Remember, Y up top is the atomic mass, P and N. Z down below is atomic number, P. So P is going to be 15 because it is the atomic number of 15. Okay. So this 15 here goes there. Y is P plus N. Well, Y is 32. If you know P is 15, can you do the math on N? Okay, apparently I couldn't because I didn't type it, but it's right there. 17 equals N. All right. As far as the charge goes, this is easy to calculate the charge. Easy by being more simple than what we're going to do. Okay, not necessarily that everybody could do it. But the 3 negative charge here, the only way you could tell the number of electrons that are present is if you know the number of protons. So first thing you gotta do is just pretend it's neutral. If we knew the protons, which we do, that they're 15, then if it was neutral, then you'd have 15 electrons. Okay, 3 negative means we have 3 extra negatives, so we gain 3 electrons, and 15 plus 3 is 18. So we had 18 electrons for that phosphide. The gig about oxidation numbers, which I kind of want to hit at, and don't get too bent out of shape about them, because when you really start playing with oxidation numbers and oxidation reduction reactions, which comes later, you really get a handle on it. So just get this idea that, hey, we have molecules. Molecules don't have charges necessarily because electrons aren't lost or gained. They're supposed to be shared. But if you've ever shared a cookie, like little kids are great for that, break it in half, someone says, I want the bigger half. There's always a bigger half because you can't break it perfectly in half. Sharing isn't always equal. And in SO2, and you have a sulfur with electron pair on it, bonded to two oxygens. Okay, those bonds here represent electrons being shared. Well, oxygen's a bit of a bully. He's going to pull more electrons to it, so the sharing won't be equal. Already, and so if you look at oxidation numbers, the sulfur is a +4, each oxygen's a -2. So you got a +4 down on the sulfur, each O is a -2, and so if you sum those up, you end up with 0, and hey, we had a neutral molecule. So it's cool. Oxidation numbers always add up to the charge. And I thought, if you say, wait, you just said it's 2 positive, not +2, and here you go, writing pluses first. Exactly, because they're oxidation numbers. They're parent charges, which is why they're written backwards, so that you can look at what you're seeing and know whether it's the charge or the oxidation state. Sometimes it's the same thing, but a lot of times it isn't. Okay. Here's what I've said about the charges being adding up to the oxidation numbers equaling the charge. All right. A couple quick definitions for you. All right. Before we said a cation is a formed from a loss of electrons. Well, that loss of electrons is oxidation. That's why, like, if you've seen metal rust and then it's no longer the same gig anymore, because you can easily kick through a piece of rusted metal, okay, but you can't kick down the hard steel, okay. But when it's rusted, it's different. The loss of electrons changes all the properties, okay. So oxidation, loss of electrons. Reduction would be like that fluoride I showed earlier that gained electrons, okay. And oxidation reduction is really, really useful. Batteries are oxidation reduction reactions. That loss and gain is just separated with a electrical wire, and there's electrons being lost and gained or moved down the wire. More about that in electrochem, okay. You have to be able to determine oxidation numbers. There are some rules for these. Group 1, the first column of the periodic table is always a +1. The second column is always +2. The third column or group is a +3, except for thallium. Hydrogen is usually a +1. Don't worry about hydrides right now. Oxygen's usually a -2, -1 in peroxide, so don't sweat that too much. And because the charge always adds up to the oxidation number, if you have a single atom, then the charge is the oxidation number. So copper 2 positive is an oxidation state of +2. All right. Usually have to calculate the oxidation number. And I like to wrap this up by just doing a couple quick calculations. If you had sulfate, SO42 negative, okay, if I said, hey, the sulfur is a +6, each O is a -2, then you would say, hey, well, I have it right down here, +6 plus 4 O's at -2, that's +6 plus a -8, so the charge would be -2, and it's kind of cool. It adds up to the charge. So I don't want to prove that to you in case you're doubting me for some reason, okay? But let's look at sodium perchlorate, okay? It's a nice oxidizer used in like rocket fuel and stuff. You got sodium perchlorate. Sodium's in group 1, so Na sodium. Natrum is the Latin or Greek or whatever. All right. If you're going to do those, well, from earlier, sodium's group 1, so he's +1. O is going to be a -2. Cl you got to calculate. Cl can vary. It has a bunch of different oxidation states available to it. In this instance, it's in its highest oxidation state is +7. What you would do is just say, hey, just like we did for sulfate, an S plus 4 O's added up to the charge. Well, now we got an Na plus Cl plus those 4 O's, coincidence, adding up to the charge. Well, there is no charge. That's a 0. I'm only going to point this out really fast for a reason. What's the exponent on X in math class? The exponent's 1, right? What's the subscript on the O in H2O? It's a 1. Well, what's the charge when nothing's written? 0. Because the charge is the net number of positive protons, net number of electrons. Well, if there's neither one, then you're saying you have 0 excess of protons or electrons. Alrighty, that's why you know it's a 0. So if you do the math, chlorine's going to be +7 because each O is -2, so that's -8, plus the sodium +1. That's going to give you +7. I know I hustled up to the oxidation numbers, but you just had to get a feel for it at this point in time, knowing that the charge is dependent upon the protons and electrons. Electrons on the outside, they're the things that are changing. If you get that, then you're home free. So have a good time. I'll definitely talk to you later. Take care.